Assalamu alaikum. So today we'll be continuing with our organic chemistry. In our last lecture, we were studying about the free radical substitution of the benzene molecules. We'll be going with some other reactions as well. We'll be learning today some other reactions as well. So in our last class, we saw in the last part which we saw was the further substitution, or the if let's say benzene was already being substituted with any of the electrophile, then in the preceding reaction, further free radical substitution, or sorry, not free radical substitution, further substitution or electrophilic substitution can occur. So basically, if let's say chlorine was added, so since the number 2, number 6, and the number 4 carbons are free, they can be the host carbons in order to proceed the reaction. So they will be the ones who will be helping to initiate and happen the reaction. So the final results could be CH3Cl or CH3Cl. Either they both are the identical molecules, just like what they're the mirror image of each of them. But if let's say this has been formed already, then if we again add further chlorine, the component is going to be CH3Cl, and now we have two possibilities, either here or here. So let's say we have the chlorine added over here, or we can have the next chlorine over here, CH3. Okay, let's not give or, because the thing is, this third one, it tends to form when the other two are filled. Okay, so that's the basicity, or you can also draw it in this way. Let's not make it complicated. Just yeah, I guess this will be much more easier to remember. So let's not make it complicated, and they will be giving you marks. So Cl, and this is if more chlorines are added for reaction, electrophilic substitution reaction, and this will continue until all of the second, fourth, and the sixth number carbon are bonded with a chlorine atom, or other atoms. If we provide, let's say, if in case of chlorine, we provided, let's say, an halogenoalkane, so CH3Cl or CH3Br, or some other halogenoalkanes. So that will be forming this electrophilic substitution reaction with this second number carbon, fourth number carbon, and the sixth number carbon. Okay, so that's basically it. Now today we are going to see that if let's say we already have a benzene molecule with this, it underwent some free radical substitution. No, sorry, I'm really sorry. We are going to actually study to the free radical substitution. That's why I'm repeatedly recalling that we are going to if free radical substitution has been taken place. But the topic which we will be covering now is free radical substitution. So what I tried to, or what I was trying to say, that if a benzene molecule has already undergone electrophilic substitution, in this case it was Friedel-Crafts alkylation. So after it went Friedel-Crafts alkylation, it has been it has formed, or it has undergone the reaction of electrophilic substitution. Now let's say I'm adding chlorine, further chlorine, but this time the conditions are now changed. In electrophilic substitution, what were the conditions? I need to add anhydrous AlCl3, isn't it? So that were my conditions. That was for electrophilic substitution. Remember, okay? That's for benzene. Now, if the conditions are changed, so you need to remember this for every moment, every single moment of while you are revising organic chemistry, you have to recall this condition. This slight condition change can cause a dramatic change in the reaction. So now instead of those condition, if I apply UV light, so ultraviolet light is now being provided, or if the reaction, if let's say these two components are being placed below sunlight, what is going to happen is now they are going to undergo free radical substitution reaction. Remember what is free radical substitution reaction? It was if we have an alkane, alkane, and if we provided chlorine in under UV light, they tend to have free radical substitution. Since alkane does not have a double bond, we have to replace it. Like the bonds needed to be replaced. So any of the bond is going to get replaced with a chlorine. Like hydrogen carbon bond is going to get replaced with a chlorine. Same thing is going to happen here, but the catch is none of these carbons are going to react. Rather, only the carbon, or only the part which is like out of this ring, out of this benzene structure. So this is the benzene structure. So the parts which is out of this benzene structure, and out of this benzene structure is only this already like methyl. So that methyl is going to simply undergo the free radical substitution. That means this will be our product now, CH2Cl, since one of the hydrogen is replaced, and the other hydrogen, like the hydrogen which has been replaced, that is going to form bond with the one of the other chlorine. So their radical has been formed. We know the mechanisms. So I would urge you to like go back and see the mechanism for our free radical substitution, which is actually being taught in like AS level. So the contents from the AS level, I would urge you to have some revisions on that, and we will be like in future we'll be having sort of a crash course or some review contents on the AS level contents as well. So yeah, for right now, this much knowledge is enough. So that's the free radical substitution I've been talking about. Also in last lecture, I mentioned how free radical substitution actually happens. So that would also might help a bit. Now, if let's say instead of just Cl2, let's say 2 mole of Cl2 was given. Now what would have happened? So what I tried to say, if instead of like CH3, we provided now 2 mole of chlorine instead of 1 mole of chlorine under the same condition UV light. Now what would have happened? It would have considered 2 of the hydrogen to be replaced. So 2 of the hydrogen. So that means each mole of chlorine is able to move each hydrogen. So 1 mole of chlorine molecule is able to substitute 1 hydrogen atom. That means 2 mole of chlorine is able to substitute 2 mole of chlorine is able to substitute 2 hydrogen atoms. So that means this will be left with CH and Cl2, and the other portion is HCl. That there 2 hydrogen chloride is going to be now like going out. So that will be like, so no new component or new, let's say, eliminated product. And in case if we, let's say, 3 chlorine was provided, in that case, all the hydrogen would have been replaced by this chlorine. So there wouldn't be any more hydrogen. So CCl3 would have been formed. Now, if you say, what about 4 chlorine? In that case, no more reaction would have been occurred, because there is no more hydrogen in the reaction to be replaced in free radical substitution. Point to be noted, I'm not talking about Friedel-Crafts alkylation right now. It's free radical substitution. So I'm sorry, like not the free radical, the electrophilic addition means electrophilic substitution. I mean like for the Friedel-Crafts alkylation. So Friedel-Crafts alkylations actually fall under the reaction which is electrophilic substitution, which is like the characteristic reaction of benzene ring. So here I'm talking about like electrophilic substitution is not taking place, rather free radical substitution was taking place. So no more free radical substitution would have been occurred if 4 chlorine was added. I mean 3 of the chlorine would have been replaced. Okay, now the extra mole of chlorine, if like I mean if let's say 4 mole of chlorine have been provided, the 3 hydrogen would have been replaced by 3 chlorine atoms, 3 HCl would have been formed. Now 1 extra chlorine molecule would be left over. Why? Because there is no more hydrogen to be replaced with. Okay. Now, the oxidation in the side chain of the like, benzene ring. So this reaction, the name of this reaction was free radical substitution in the side chain of the benzene. So side chain reaction. Side chain reaction means that, like, what do we understand by side chain? Like normally when, let's say, we apply some sort of cosmetics or creams, we tend to notice if it has some side reaction or not. That sort of thing, like that sort of defines the concept that we are concerned about, or we're talking about the reaction which is not part of the main duty of the product. So let's say if we are buying a product, or let's say a cream, the main function of the cream is like to, let's say, moisturize the face, something like that. The side reaction part is, okay, is it going to have some, let's say, skin allergies, or like is it like reactive to skin allergies, or is it like reactive to some type of like skin or something. So that's the part like side reaction is. So here also, this is the main component, like main part of the benzene molecule. Okay, so this is the main benzene structure, and this is the side chains. Like these are the like parts which are not actually part of benzene, though they are bonded, but this is the part which is not actually the like the inner part, or the like implicit part of the benzene molecule. So they are like the side chains of the benzene molecule. Now, as I was mentioning, that the oxidation could have happened in the side chains of the benzene ring. Now, let's say this is the side chain, and in this side chain, let's say we applied like manganate ion. So manganate ion could be like, we have like gotten it from, let's say, KMnO4. If like this is the solution we have been provided, like we provided with. So from this solution, we will be able to like extract, or we'll be able to get MnO4 minus ions. So this MnO4 minus ion, if we provide it with like in alkaline solution, so hydroxide have been given. So any alkaline solution, I'm just, for the general term, I'm mentioning the ions which are the crucial part of this reaction. So instead of KMnO4, you could have been like provided with NaMnO4. So the main concern is we need this MnO4 minus ion. So manganate ion is required, and for this hydroxide, we could have provided it with sodium hydroxide or potassium hydroxide, or anything like any alkali we could have been provided with. But the main concern is about like we need the hydroxide ion to react it with, and the manganate ion. So when these are like provided, and the like it is made to undergo heat under reflux. So heat under reflux, the product is going to be carboxylic acid. Simply the chain, the alkyl group, it is going to get oxidized. So this is actually oxidizing, and this is the oxidizing reagent. So manganate O4 in alkaline solution is the oxidizing reagent. This causes this side chain, or the part which is outside of this, or the alkyl group, the alkyl group, this is going to be get oxidized, form carboxylic acid. In addition to that, carbon dioxide and water is going to be formed as byproducts. These products, which are like not the main products, they're like the result of the reaction, like side reaction, like the result of like these are the extra products. Okay, these are the extra products which we are getting. These are known as the byproducts. So byproducts. Now this is a carbon dioxide and water as the byproducts. Another approach could have been taken place. Instead of, let's say, this was the like condition 1. So if another condition would have been like provided, so instead of all this, if let's say we provided it with just simply H plus, that means if acidic condition was provided. Okay, so if acid instead of this manganate ion in alkaline solution, if let's say we provided it with acid, then simply this carboxylic acid, sorry, this shouldn't be H3, it should be only H. So this carboxylic acid would have been formed. So if instead of this first condition, this second condition is provided, simply the same reaction would have been occurred. Now let's say, say a second example could be similar sort of like example could be, let's say, C2 CH3. Okay. Now let's say either of the condition has been given. Okay, Mn of MnO4 minus plus OH minus. Okay, heat under reflux, or let's say the second condition, which was actually H plus. So either of the, like, you don't need to write both of them, just write any of the condition you prefer. Okay, so I would say go with this one, but also know that if acid is being added, they also tend to show oxidation reaction. Now, if this reaction is taking place, now can you guess what sort of, like, what product could have been formed? Just pause the video and like try to see if, like, try to guess by yourself what reaction might, or what product could have been formed. So I'm going to say the answer right now. So in this situation also, simply the one carboxylic acid is going to get formed. So by, like, with this, there will be the byproduct of carbon dioxide and water. But what can you understand from these two reaction, like from these two examples, one at the top and one at the bottom? In both the cases, what, like, it doesn't matter whatever the, like, how long the alkyl group was and whatever the alkyl group is, if these conditions are provided, the side chain, this side chain from the starting point, it is going to get, like, transferred into a single carbon carboxylic acid, just like COOH will be, like, replaced. The whole side chain or whole alkyl group is going to get replaced with a single COH group. Okay, so that's what it means. So I hope you understood. The next part, we can, let's say, oh, don't get confused over here, which is like, if you want to write it in this way, let's say, wait a minute. What I tried to mention was over here, this H plus means instead of this hydroxide, okay, this alkali, if you provided this, I mean, if you, instead of like this OH minus, if you provided H plus with this MnO4 minus, okay, so there are two types of oxidation. One is alkaline solution, like alkaline oxidation, and another is acidic oxidation. So instead of this alkaline oxidation, if you provided acidic oxidation, which could be written like this, let's say the first reaction, let's say we're writing it like this. So CH3. So writing KMnO4. So I'm also right, like, if you wish to write Mn instead of MnO4 minus, if you wish to write the actual solution which you'll be trying to provide, also you can write that. Okay, so KMnO4 or writing just simply MnO4 minus, both are correct. Now, like, what I meant by H plus is, if with this I added H plus, okay, instead of OH minus, I'm adding H plus with heat under reflux. Okay, so the product is going to be the carboxylic acid. So that's what I tried to mean by writing the two conditions there separately. Now, let's do a couple of examples, like sort of like the questions that which appears in the actual exam. So let's say they have given you this benzene, and they have provided you CH3Cl, AlCl3 with anhydrous condition, anhydrous. I hope you are, like, actually getting it, like where this reaction is going, like where this is having its way. So where is it going? So in the, like, this condition is going to produce some sort of product, and from that product, when we add Cl2 in UV, from there we will get, or we would get, some sort of other product. And on that product, if we apply, let's say, KCN, which actually we didn't, like, we didn't do, like, officially, but that is part of our AS contents. So KCN, but we obviously, like, I obviously, like, shown it on the last lecture. So if you need help, you can see, or you can go there and try to see what reaction could have been happened over here. Oh my God, I'm writing the answer. Sorry for that. So they are going to mix the topics they're going to mix the topics from AS and A2 as well in your like A level AF exam, CH2 COH. I mean, like in A2 exam. So, oh yeah. So this is the final product, and the last condition was, let's say, H plus aqueous, heat under reflux. Okay. Now try to guess what products could have been formed here. No need to like worry about this product. This could be actually like you can also get this by yourself. Like you can also get this done by yourself if you like follow the reactions for like if you revise the organic chapter, organic compound or organic chemistry chapter of the AS level by yourself, so you'll be able to like understand what reaction have been like what is actually taking place over here. So don't worry, I'll be helping you in a short while. So I would urge you to like pause the video and do it by yourself. So here actually we are actually doing what? Benzene ring having a reaction which is Friedel-Crafts alkylation, isn't it? Remember, there were like two conditions. One was FeCl3, another was AlCl3. Okay, so here we have AlCl3, which is the condition for Friedel-Crafts alkylation. While FeCl3 was there, like in our first lecture of organic chemistry, we saw FeCl3 being used. That was actually a normal reaction, but electrophilic substitution reaction that is mostly used for like only halogens, like so Cl2, Br2, only that sort of molecules. Like for them, this FeCl3 like is being used. That has no specific name, just electrophilic substitution reaction. But another reaction from electrophilic substitution is this Friedel-Crafts alkylation. I keep on forgetting the name Friedel-Crafts. So Friedel-Crafts alkylation. After this reaction has been formed, you have the product which is CH3. Also, you can give this CH3 in any of this carbon. So you can like instead of like by not giving it on the like top level on the like carbon number 1, you could have also given it, let's say, over here CH3, or you could have also like given it, let's say, on the like bottom carbon CH3. Any one would have like happened. It would have been correct, but you need also to like you also need to see that is the last product or the product which they have given in which number carbon is our chains are, the side chains are. So if it is on the topmost carbon, so it is better for you to give the carbon or make the side chain or alkyl, add the alkyl group on the topmost carbon atom. Now from here we are observing they are giving a Cl2 UV. This is the condition for what? Free radical substitution. So since free radical substitution is happening, CH2Cl is going to get formed. CH2Cl is going to get formed. Now, since they haven't mentioned us how many moles of chlorine is being added, just consider 1 mole is being added and write it like accordingly. Now, from this Cl, from AS note, if you see our AS contents, if you see that halogen, when they react with cyanide ion, they tend to form this sort of molecule, which is like replace this cyanide ion, they replace the chloride from or chlorine from this bond, carbon chlorine bond, and form CH2CN. So this is the new bond which has been formed by replacing the chlorine. We don't need to write the side products in this case. So we don't need to like the byproducts in this case. Over here, hydrogen chloride has been formed. Over here, another hydrogen chloride or KCl, sorry, for potassium chloride is being formed. So you don't need to write this at this moment, because they are just asking us to write the main products. So these are the main products. And now see that when H plus is added, heat under reflux, so that means this cyanide ion that is being reduced to form carboxylic acid. Okay, so that is forming carboxylic acid. Give me a second. Let me see actually what is like, is it actually like reduction or the hydrolysis? So this is actually hydrolysis reaction. I'm really sorry. This was actually hydrolysis reaction. So by like for simplicity, you can write like which sort of reactions are there. Hydrolysis reaction is taking place here. Over here, this is free radical substitution. Here it is, let's say, electrophilic substitution. Also, you can write like that this is actually like a specific reaction which is Friedel-Crafts for IEDL Kraft alkylation. So I'm writing in short. So these are the reactions happening place. For the Caesian part, just a minute, let me see, like to be sure what sort of reaction is it. Alkaline hydrolysis of nitrile compounds makes all okay, reflux nitrile compounds. Okay, fine. And so this is like basically just formation of nitrile compounds from halogen alkene. Nothing else is like mentioned here. So this was actually like halogen reacts with Caesian, and the conditions are like usually they like provide ethanol to make the like Caesian. Like the solvent is used as like the ethanol is used as a solvent. Okay, so in over like over there, but in the reaction, like in the question, it hasn't been provided you with, but this is the like product which is being formed. Now let's say we have another reaction. So another reaction, let's say, is like same example, like same sort of example, let's say. So they have given you with, provided you with, let's say, this is the organic substance. They have given you CH3COCl and AlCl3. So this is anhydrous. Here will be some product form. From here, they're applying HCN with KCN. There will be some other product being formed. And from here, when we add H plus aqueous reflux, this compound will be formed. You can take help from the previous example as well. CH3, this is the final product being formed. COOH. So you can pause the video and do it by yourself. And I'll be saying it right now, what will be the reaction or what will be the product. So this is the product. Friedel-Crafts alkylation, that means this LCO3 is just going to replace this chlorine, okay? And the rest will be the electrophile. So here we will be left with C double bond O CH3. Then we will be like, for understanding, I would suggest better to have like revise the start like previous lecture you'll get the like how this product is been formed. Then if we add HCN in KCN, like HCN and KCN is our catalyst. So when this is provided as the conditions over here in this component, the products will be this ketone group. This is a ketone group. So this ketone group, it will get reduced. Reduction is now going to happen, and this there we will be getting this carbon forming alcohol group. We will be having a cyanide group, and we'll be having the CH3 group, which we already have. So this will be remaining. This ketone group, C double bond O, will be transferred into this alcohol group, and new group bond is going to be added, which is cyanide. So reduction is going to take place. And when we add H plus in reflux, we already saw in the last example that this cyanide get hydrolyzed. So this is an acidic hydrolysis of the this nitrile molecules. This is due to this presence of cyanide. The molecules are also known as, this compound is also known, like you can say this is a nitrile compound. So this is a nitrile group, or you can say a cyanide group. So that causes this formation of carboxylic acid. A couple of more examples could be that, let's say we have normal concepts from our let's say AS. So if CH3 is there and we provide you with Cl2UV, we would get some product. And when you apply NaOH, so this should be helping you to revise the AS concepts as well. NaOH, so under reflux, some other components you will be getting. And when you add with it H plus with, let's say, K2Cr2O7, and heat under reflux, obviously heat under reflux, and you get certain other product. from here, when you, let's say, apply HCN with KCN, you would get some other product. And when you add H plus reflux over here, you get, let's say, this is your final product. Okay. I would also urge you to pause the video and do the examples by yourself, because I will be showing them in just a moment. So now on the topmost reaction here, Cl2 plus UV, actually the conditions are. So this is, we can just by observing the reaction, we can say this is a free radical substitution. So we'll be having CH2CH2Cl, and over here when sodium hydroxide is added with reflux and aqueous condition, this chlorine, it is going to get replaced by this sodium hydroxide. So CH3CH2OH. So this is basically having nucleophilic substitution reaction, because halogen alkane undergo nucleophilic substitution reaction. Now, when we apply H plus with K2Cr2O7, this is actually an oxidation reaction where this alcohol will be oxidized. Now, since this alcohol is a primary alcohol, I would also urge you to have a clear vision or clear concept on the concept like which are the primary, secondary, and tertiary alcohols. So, since this is a primary alcohol, after oxidation, we will be getting CH3CH2 CH3COOH, CH3COOH, and in this CH3COOH, I mean this. Okay, actually, I made a mistake here. This condition would be heat not under reflux. So if this was given that heat under reflux, then carboxylic acid would have been like, that would be correct. But since the condition is mentioned heat not under reflux, not under reflux, that means instead of carboxylic acid, a carbonyl compound will be produced, which is in this case aldehyde. For group 1, the primary alcohols, carbonyl compound, in place of the carbonyl compounds, aldehydes are formed. So from primary alcohol, aldehydes are formed. So when in aldehyde, we apply HCN with KCN. In the previous example, we saw that the double bond group, this double bond group of carbon oxygen in ketone or in aldehyde, they tend to form this, they tend to break the bond of carbon oxygen double bond, forming alcohol. That means reduction is taking place, and the cyanide is being formed, CH3. And over here, when H plus with reflux is added, this cyanide is hydrolyzed. So acidic hydrolysis is happening here to form carboxylic acid. Now, let's go to the next example, which could be, let's say, another benzene ring. In the benzene ring, let's say we are adding CH3Cl with anhydrous AlCl3. Some product will be formed. Cl2UV is then added. Some other product is going to get formed. Then we will be having, let's say, sodium hydroxide aqueous with reflux. So I'm just writing in short for the time constraint. So heat under reflux. Then some other form will be formed, or other product will be formed. Then in this condition, let's say we added H plus K2Cr2O7, heat not under reflux. So always do remember the conditions and observe the conditions with full concentration, because a slight change in concentration can have a drastic change in the reaction type. And this will be our products. And finally, H plus aqueous with, say, reflux. Our final product would have been, let's say, carbon, hydrogen, alcohol group, and a carboxylic acid group. Okay. Now, I would also urge you to pause the video and do it by yourself. In the first reaction, we are seeing it is a electrophilic substitution, or more specifically, a Friedel-Crafts alkylation. So this will be our product, CH3. And now we can see the second reaction is free radical substitution. Free radical substitution, which with the chlorine, presence of chlorine is being added. If instead of chlorine, let's say bromine was here, the simple, everything would have been same. Just instead of chlorine, we would have written here bromine. Okay, since here we have chlorine instead, so we'll be writing chlorine here, CH2Cl. Now from over here, if we add sodium hydroxide, this is actually nucleophilic substitution reaction in halogen-alkene. So sodium hydroxide, the hydroxide is going to replace the chlorine over here. So it will be CH2OH. So that means an alcohol is formed. This alcohol is a primary alcohol. So when H plus K2Cr2O7 is formed, like reacted, and heat not under reflux is done, we would be getting a carbonyl compound. But this case, it's this is a primary. Primary. This is the aldehyde. So when aldehyde is made to react with HCN in KCN, the products are simply carbon with hydrogen is here, and OH and C and cyanide. So that means reduction is happening. And when H plus with reflux is added, the cyanide gets acidic hydrolysis undergoes and carboxylic acid is formed. So that's all for today. And we'll see you in the next lecture. Take care.